Yeah, there's plenty.
Hello, everyone. That's a great entrance from me. I'm Alok Jha, the Science and Technology Editor at The Economist, and I can't walk upstairs. This is Jeremy O'Brien, who is the Chief Executive of PsiQuantum, and he's going to be telling us about his vision for useful quantum computers. And as you've heard, that's defined as utility-scale fault-tolerant computers. And we've got 15 minutes of discussion. So we're going to talk, and then there's going to be some questions. Hopefully you'll ask some questions, and you know how to do that with the hashtag, and it'll appear here. And then we'll wind on to the next one. So Jeremy, I think that even though this is an expert audience, it's good to get everyone grounded with the information. A fault-tolerant computer. First of all, let's define what you mean. What do we mean by faults, and why do we need to be more tolerant of them, or make computers that are more tolerant of them?
Yeah, sure. So, things go wrong in a regular computer as well, but they go wrong at a rate that's so low that we typically don't have to worry about error correction, let's say in a CPU. If, however, you send them into space, you do have to worry about those errors, and you have to encode against those errors because the cosmic rays that cause errors, you're no longer protected by the Earth's magnetic field. And the idea in both cases with a conventional computer and with a quantum computer is pretty simple, which is that you build in redundancy. So you have a logical bit or a logical qubit that's encoded in multiple physical qubits to get the error rate sufficiently low that you can run a computation for long enough to do something useful.
An error here just means, some mistake or calculation thing which then can propagate throughout the system so that the end result is something useless. That's the problem with these. And in quantum machines, you're going to get that just because of the fact that they're hard to build, essentially.
That's right. So in your iPad there, the transistors have an error rate of something like 1 in 10 to the 20. So it's so low that, operating at a gigahertz, over minutes, you don't see those errors. Every now and again, you might find a glitch. And a quantum computer is a bit trickier because it's an intrinsically hybrid analog digital system. So the beauty of digital conventional computing is that you're encoded digitally, and you have a high and a low voltage, and you can sort of latch back to those voltages as things dither around. With a quantum computer, you can convince yourself pretty quickly that it's a hybrid analog digital system in the sense that when you measure a qubit, you measure a 0 or 1, and that's your output. But prior to that measurement, it can take a continuum of values, and so in any analog system, you can only set things to within some precision. And so there's an intrinsic issue with errors. And then in addition to that, there's also error rates not dissimilar to the cosmic rays.
And so in the normal discourse around building quantum computers that one hears, and that people in this room probably are familiar with, people are trying to build more and more qubits into their machines, quantum bits, in different ways. These are obviously error-prone. And the sort of headlines you get are, a new quantum computer with this many qubits, it can do these things. You've taken a slightly different approach in your company. You want to build one that's useful, in other words, that can be tolerant to these faults. So first of all, why did you take that approach? And then how do you do that? What's the sort of focus in the way that you're building your quantum computer?
Yeah, so we took that approach because it was our belief that all of the utility, all of the commercial value would come with those large-scale systems with error correction. And that was based on some technical understanding and was also a bet, as you have to make. And our bet was that, there will be no utility in those small, noisy systems that we have back then, and indeed today. The utility will come with these very large error-corrected systems. And indeed, that has been a more controversial topic than it ought to have been, in my view, in that I think that actually has been the wisdom for 25 plus years, that you need to implement error correction, and you need a very large quantum computer in order to do that. And there's been an era of so-called NISQ, noisy intermediate scale quantum, where there was a lot of what I would say is unwarranted hope that people could find utility in those small noisy systems. So we didn't go down that path. We went down the path of figuring out how to build a really big quantum computer that would have utility.
And so this is really about, as you say, utility. It's about bringing what's a research and development idea, something that's just a case of breaking records and so on, into being able to solve real problems in the world. Okay, well, in that case, tell me about the computer you're building in Brisbane. So in 2027, there will be, if all goes to plan, a fault-tolerant utility-scale quantum computer in Brisbane. Just describe that machine for me. Why there, and what will it be able to do?
Yeah, so I'll describe it to you. So it's a system with, let's say, of order 100 cabinets that are the equivalent of the 19-inch racks that you find in a data center or a high-performance computer. Each of those is filled with hundreds of silicon chips. Half of them are photonic, half of them electronic. That's all wired up electrically as well as optically using conventional telecommunication fibers, and then cooled to very low temperatures. And so actually, at several levels of detail, it looks very much like a data center or a high-performance computer. And indeed, that has been the ethos of our approach, is that we have set out to leverage the semiconductor industry in full, so both at the chip manufacturing level, but also at the system assembly level, to deliver that system. So it's a large facility, and that system will be able to address these problems that we think are of extreme value that only quantum computing will be able to address, spanning, a multitude of industries that I could go into. My favorite domain is in sustainability, so the prospects for designing next generation solar cells, better electric batteries, green hydrogen processes.
Well, let's go into this a little bit more. We'll talk about the platform in just a moment, but just those specific uses, because I feel like that would makes the sort of whole technology come alive a bit, because at the moment people talk about quantum computing just as an end in itself, but of course it's there to do something useful. So give me an example of some sustainability uses where a quantum computer will do better than a traditional one.
Yeah, absolutely.
And your specific one in Brisbane.
Yeah. So I totally concur. It's to do something useful, and indeed that's why I've been at it for 25 some years. Is to figure out how we build it, but then what we do with it. And I think this is very much the starting line, as far as I'm concerned. When we have such a large scale system, then we can actually use it for really compelling applications. So I'll give you a couple of examples from the sustainability space. It turns out that although everyone, as far as I can tell, has a lithium-ion battery in their hand right now, we don't understand how those things work, and nor will we ever be able to simulate the chemistry in those batteries on any conventional computer that we can ever build. So it turns out that there's some chemistry at the interface between the electrolyte and the electrodes in that battery. They form some sort of mirror charge that prevents the electrode from being torn apart when you switch it on in ways that we don't completely understand. Now, that hasn't stopped us from deploying lithium-ion batteries. Every now and again you see an electric car on fire on YouTube, or you're forbidden from taking a particular brand of laptop on a plane. But it is a huge impediment to designing better batteries, obviously. If you don't understand how your latest, greatest technology works, actually, then you're really impeded in designing next generation. So that's one specific example, and it's one example across a multitude that falls within molecular simulation, material simulation, and so on, which spans not just sustainability, but let's say the pharmaceutical industry, where you have a very analogous problem. We have drugs that we consume,
which we don't know how they work. Yeah.
Which we don't know how they work. Furthermore, that's an industry that we should see for what it is. It's broken. It takes a decade plus and billions of dollars to more often than not fail to bring a new drug to market. And even when we succeed, its efficacy is somewhat, maybe it helps a bit. And a big component of that outrageous sort of picture is that we can't simulate the molecules that we're putting into our body, never mind the molecules that they're interacting with, nor will we ever be able to do so with any conventional computer that we build. And if you want a kind of a proof positive on this across the board, I would point to Mother Nature. Mother Nature has the same chemistry set that we've got given, right? Now, we humans are a bit prone to, thinking that we already live in an advanced technological age, and we always have throughout history, and we've got all this mastery over science and engineering and so on. I didn't see us doing anything very comparable to what Mother Nature does with chemistry after billions of years of evolution, materials that grow from small seeds and consume things, photosynthesis, nitrogen fixation, etc., etc. And I don't believe that we will be able to even get into the same league until we have a quantum computer to be able to, if you can't simulate the building blocks of the world that you find around you, never mind the building blocks of the world that you're trying to engineer, that's a pretty hopeless situation. And in my head, there's a cartoon of a blacksmith's workshop, hammering and tonging an outcome, supersonic aircraft out of that situation. That's what we're trying to do with materials and chemistry until we have the ability. And of course, I was just having a discussion earlier. We've woken up again to the fact that we live in a physical world, and that everything physical at heart requires a chemistry explanation. So yeah, I think this is where you can start to see why there's going to be such a huge impact from this technology.
Mother Nature's had quite a long time to do all this, to be fair. So just let's not be too down on humans. That's a really great example of how to improve something very real that we need, lithium-ion batteries. I'm assuming materials science, other chemistry, pharmaceuticals, these abilities that quantum computers uniquely will have to simulate quantum mechanics, essentially because of the nature of their thing, of their properties. So that's quite exciting. What's allowed you to be able to build a useful computer in such a short space of time? I mean, not many others are talking about operationalizing these things in such a short space of time. What are the sort of technological decisions you've had to make to allow that to happen so soon?
So the short history is that together with my co-founders, we spent 20 years in the university research environment trying to figure out if there was a path whereby we could use the semiconductor industry and the computer systems industry in full to make a quantum computer, because it has been my conviction for 25 plus years that we won't have quantum computing in my lifetime unless we figure that out.
And these are industries that exist, can manufacture things at great scale.
Yeah, my conviction, and I'm far from alone in this, is that that's a manufacturing capability that really is truly extraordinary. I think there's plenty of technical people here, and technical and non-technical people alike should wow themselves once in a while with what that manufacturing capability represents. We humans have a manufacturing capability that produces 1 trillion chips a year, trillion being too big a number for us to wrap our brains around, each of which contains billions of components measured at billionths of a meter. That's the result of traveling up an exponential curve for 50 years, which should be impossible, but has required trillions of investment and 50 years of development. And I was saying to you earlier, I sometimes provoke people with I feel like other human activities is the equivalent of scrabbling around in the mud with sticks and stones compared to what we can do in that manufacturing industry. So that was the short version of the story. 20 years of figuring out a path whereby we could leverage that existing capability and investment. And when we uncovered such a path in 2015, we believed we had that path. We spent several years and several $100 million to get into a tier one semiconductor chip foundry. There's only a handful of them on the planet, and they're not in the business of doing fun research projects with small startups. You've got to prove that they can really do that. And now we've been working with that industry for 4 years or so to be at the point where we're essentially mass manufacturing the chips that go into that data center like facility. So it's that leverage is the leverage is the short answer to how we've been able to move.
And it's photonics that you're using on silicon chips, which is the sort of what's allowed you to accelerate the introduction of this computer in 2027.
That's right. So it turns out that photonics is an approach that enables you to scale in large part because of the the leverage of the manufacturing, but also the connectivity and the cooling and control electronics that have to be there for a large-scale system makes it very appealing. So my co-founder Pete likes to say, forget about the qubits. Everyone's arguing about qubits. Everyone's got qubits. Everyone's had qubits for decades. They're all great. How do you get from 10 or 100 of those things to millions of those things? And the answer is those scaling challenges that I just mentioned.
Okay, final question for you. You've got 2027 as a goal. That's clearly something that's been many decades in the making, and we've heard about the kinds of things that that computer will do. Are you already thinking about version 2 or version 3 of whatever that computer's going to do?
Absolutely, we are. Yeah, we have plans for the next generation of system that will be bigger and more capable and so on. And I think we're at the start of a similar journey as conventional computing took, where we'll build bigger and more capable systems and deploy them more widely into the future.
Jeremy, thank you very much for your time. Our next speaker will be looked after by Jason Palmer, my colleague, who I will invite onto the stage now. Jeremy, thank you very much.
Thank you very much.
Thank you.